Hello, welcome once more to my physics lecture series. In this particular lecture series, I'll be looking at dynamics and by extension, forces. So when we say dynamics, what do we imply by dynamics? When you hear the word dynamics, the first concept that comes to one's mind is movement or motion. Under kinematics, we talk about motion of objects without looking at or considering the causes of that motion. But when we talk about dynamics, we are most interested in what causes motion. What causes motion? So we would say that dynamics is actually an area of mechanics that deals with the effect of forces on the motion of objects. Or we can say that dynamics is actually an area that studies what causes motion. I'll go with that simple definition. Dynamics is a branch of mechanics that deals with the study of motion. Motion of objects. And what causes an object to move? It is force. So by extension, we are now going to consider force. The general definition of force is that force is either a pull or a push. That is force. Either a pull or a push. That is the general definition of force. Now, when an object is at rest, the object will continue to be at rest except it is acted upon by an external force. So if I have an object, let's say on a horizontal plane, this is an object of mass m. For this object to move from this point, force has to be applied on the object, either to the left or to the right. And when force is applied to the object will accelerate from rest. And so that takes us to Newton's laws, because the definition of force can be actually obtained from Newton's laws of motion. So like I said, if I have a body of mass m, as you can see, and that body moves with a constant acceleration, then according to Newton's second law, the force acting on that body is F equal to ma. That is the force acting on the object. When force acts on an object, what happens is that the position of the object, its velocity and acceleration will change. So if you have a body at rest, for that body to be in motion, if you have a body initially at rest, for that body to be in motion, a force must be exerted on that body. Also, for the body to stop moving a force must also be exerted on that body. Hence, if a body is in motion and a force does not act on the body, then that body will continue to be in that motion. And having observed this phenomenon, Isaac Newton, in his wisdom, postulated the first law governing the motion of objects. And that law is universally accepted and known as Newton's first law of motion. I'm just going to state the first law. I'm going to write it on the screen. And that first law states that an object at rest will remain at rest, while an object in motion will remain in that motion with a constant velocity unless it is acted upon by an external force. Like I said earlier, Newton's first law of motion states that an object at rest will remain at rest, while an object in motion will remain in that motion except it is acted upon by an external force. Okay, so Newton's first law is generally regarded as the law of inertia. Why? Because it applies to objects in an inertial frame of reference. What is an inertial frame of reference? An inertial frame is defined as a reference frame in which an object may move at a constant velocity when it is not subjected to any force. An inertial frame is a reference frame in which an object may continue to move at constant velocity when that object is not subjected to any force. That's an inertial frame. And of course, force is measured in Newton. We said that F is ma. That's from Newton's second law. We'll state that second law later and derive that equation. So mass is measured in kilogram as the SI unit of mass, and acceleration is measured in meter per second square. But the unit of force is in Newton, so it implies that 1 kilogram meter per second square is equivalent to 1 Newton. So we can define a Newton as the force. We can say the Newton is defined as the force acting on a 1 kilogram mass and produces an acceleration of 1 meter per second squared. Of course, if we apply dimension here, the dimension of force will be ml t to the power of -2, or simply say ml all over t squared. So let's look at Newton's second law of motion. I'm just going to state that law straight on. So the second law. The second law, that's Newton's second law of motion, states that the rate of change of momentum, so the rate of change of momentum of a body is proportional to the resultant force acting on it, that is acting on the body, and of course it takes place in the direction of the force. Take that again. The rate of change of momentum of a body is proportional to the resultant force acting on it, and it takes place in the direction of the force. Now, momentum is expressed as mass times velocity and represented by the letter P. So we use P to represent momentum, which is equal to mass times velocity. And going from Newton's second law, we said that force from Newton's second law, we have agreed that force is equal to mass times acceleration. From the onset anyway, we are going to explain how that equation comes into effect. By stating the law, we have said that the rate at which the momentum of a body changes is proportional to the resultant force. So force is proportional to the rate at which the momentum changes. That will be the P over the T, since momentum P is equal to mv. So if that is the case, we can then say force is equal to the rate at which the momentum changes. Momentum, of course, is mass times velocity. So we substitute into this expression, and that gives us V into mv all over dt. But the mass is constant. So bring mass out, bring the constant term out, and differentiate the velocity. So the rate at which the velocity changes is equal to acceleration. Therefore, force is equal to mass times acceleration. So this is how this equation is obtained from Newton's second law of motion. And we talk about mass and weight. Just be brief about that. The quantities mass and weight are two different quantities. They are not the same, but we often misconstrue them even in our daily usage. Mass is simply defined as the quantity of matter that is present in a body. The quantity of matter present in a body. Why the weight is quite different from the mass. The weight is quite different from the mass in the sense that the weight of a body is the force exerted on the body by the earth. So the weight of a body is the force exerted on the body by the earth. And it is directed downwards. So that weight is expressed as mass times acceleration due to gravity. So you see there is a force. Of course, the weight of a body depends on the acceleration due to gravity g. Why? Because g varies with geographical location. G varies with geographical location. As a result of that, a body that has mass 50 kg in a location where the value of g is 9.8, we have a weight of 490 Newton. However, if we have a body that has that same mass of 50 kg in the moon where the value of g is 1.6 meter per second square, if you multiply that with 50, you have 80 Newton. So you see that here in Earth, where our g is around 9.8, for an object that has mass 50 kg, the weight will be 490 Newton, which is 50 times 9.8. But if you take that same object to the moon where g is 1.6, then 50 times 1.6 gives you 80 Newton. So you see that the weight of any object depends largely on the geographical location, and that is depends on acceleration due to gravity g. Then let's look at Newton's third law. Newton's third law of motion. This law can be stated in different variants. To every action, there exists an equal and opposite reaction, or action and reaction forces are equal and opposite, or when two bodies are in contact, the force they exert on each other is equal and acts in the opposite direction. So whichever way you want to state the law is allowed. But take note that both forces are equal and they act in opposite direction. So I will say to every action there exists an equal and opposite reaction. So I'll go with this. So if we have two objects, let's say x and y, and they are in contact, then the force exerted by x on y will be, we can just say, let's assume the force x exert on y is F1 and the force y exert on x is F2. Then we can now say that F1 will be equal to minus F2. They are equal forces, but they act in opposite direction. So we are going to apply this law to solve one or two problems. So we have a problem here. Very simple case. Assuming we have a scale pan that rests on a floor of an elevator, you place a bag that has mass on the scale pan. So let's use a diagram to illustrate this. This is like a scale pan. Okay. Is resting on the floor of an elevator. So let's assume this horizontal line represents the floor of that elevator. Then you place a bag on this elevator, on the scale pan rather. What would you say will be the reading of the scale pan when the system is in equilibrium. Now, ordinarily, the weight will be acting downwards. It will have a normal force acting upwards. And so, if in a state of equilibrium, if the elevator is moving upwards, then the force will be directed upwards. And the force will be greater than that of the weight. So, in a case of equilibrium, so this is the tension on the scale pan and the weight of the object. So at equilibrium, the tension, that's the upward force, will be equivalent to the downward force. Then in the case of an upward movement, still using this diagram, if we are looking at the upward movement, for this object or the elevator to move up, for it to move up, let me write it down. For the elevator to undergo an upward movement, T must be greater than the weight. And we know ordinarily that force is equal to mass times acceleration. So if T is greater than the weight, then it means the total force will be T minus the weight is equal to mass times acceleration. That will be our equation. And we know that weight is what? mg. Well, of course, we can as well say T is equal to ma plus w. And w is the weight, which is mg. So T can be likened to ma plus mg, which will be equal to m into a plus g. Then, for the last case, a downward movement, that will be the opposite of the case in bi rather. For the elevator to move downwards, so for downward movement, the weight must be greater. This weight must be greater for it to move downwards. So for downward movement, W, which is the weight, must be greater than T. So we can now say that the total force will be W minus T is equal to MA. In that case, mg minus T is ma. So that mg minus ma is equal to T. Therefore, your T will be what? M into G minus A. So this will now be the reading of the scale pan if the elevator is undergoing a downward movement. This will be the reading if it's undergoing an upward movement. And this will be the reading when it is in a state of equilibrium. We are yet going to consider another example that has to do with a pulley system. We'll look at a pulley system and also apply this concept that we just applied in this simple case. Now we have a simple example. Here we have a block. We are told to assume that a block that has 5 kg is attached to a string or spring. And is passed over a frictionless pulley. So having this now, if the other end of the string attaches to a 12 kg block which lies on a frictionless floor, we ask to compute the acceleration of both blocks and also the tension in the string. Now, this is a very simple case which we can just easily calculate, acceleration and the tension. But then we have to use a diagram to illustrate the information. Once we use a diagram to illustrate the information, it becomes more easier to handle. We can as well have the diagram attached to the question, but in a case whereby you don't have a diagram explaining the question, you on your own, you have to visualize the diagram, draw the diagram, and use that diagram to answer the question. So let's go on. In this case, we'll look at the question point by point and draw the diagram. So in this case, we are told that a block of 5 kg is attached to a spring, or a string rather. So let's get a block. Let's say this is the block. Let's assume this block is lying on a plane. So 5 kg. Okay. Let's read the question all over. Assume a block of 5 kg attached to a spring is passed over a frictionless pulley. If the other end of the string attaches to a 12 kg block which lies on a frictionless horizontal floor. So this 12 kg block is lying on a frictionless horizontal floor. So it's on a floor. Of course, it is attached to a pulley system. So this block is attached to this system, which is in turn attached to another mass, 5 kg, that is hanging on that spring. So this is a 5 kg mass. So let's call this mass M2. We call this mass M1. Now, if you check, since this is a pulley system, if you are pulling it down, it means the acceleration of this block M1 will be to your right. So the acceleration will be to your right. Of course, our tension of M2, that's the tension of the rope pulling up, is this. So we move on to say, okay, looking at the diagram now, you see that it fits perfectly the information given. This block of 5 kg is attached to a spring that is passed over a frictionless pulley. To the other, if the other end is attached to this 12 kg, so the other end of this string is attached to the 12 kg block lying on this horizontal floor. Now we are left to compute the acceleration of both blocks. How do we do this? First, we must use a free body diagram. First, we use a free body diagram. To illustrate that. What do we mean by free body diagram? These two blocks will represent them by just a dot and indicate all the forces acting on it. So this is our mass M1, which is a 12 kg. It is resting on a floor, so it will have a normal force, have a weight. Then the tension on this string is in this direction. Then we go on to the mass M2, which is hanging from the tension. So this is the mass M2. This is the mass M2, which is what? 5 kg. Then the tension is acting upwards. So our weight is M2G. We have the tension acting upwards. So on this mass of 5 kg, we've indicated the tension is acting upwards, the weight is acting downwards. Then for this, the tension is acting this way. So we'll consider for the first particle, that is particle 1. So for particle 1, just say block 1. Let's not be different. For block 1, T1 is equal to, or we just simply say T because it's the same time, okay? T1 is equal to F1, which is what? MA. This is T. There's no external force acting on this string apart from this tension T. So it means the only force acting on this string is T. So that's why we say T1 is equal to F1, which is MA. But since we are dealing with particle 1, it will be the mass of particle 1 times acceleration. Then for particle 2, which is block 2, that's the 5 kg. We have that since it is hanging, if we are pulling this, we have identified now that we are pulling this pulley. If we are pulling it down, for this pulley to come down, it means the weight must be greater than the tension on this string. So in that case, you say our weight minus the tension is equal to F2. We can as well remove the 1, but I intentionally fixed this one here so that we won't get confused about this tension. But the tension on this string is the same tension on this string. So we can as well use the subscript 1, or we remove the 1. So now what is our weight? Our weight is mass of this M2, that's the second block, times G. So we say M2G minus T1 is equal to M2A. Why is it M2A? Ordinarily, force is mass times acceleration. So if you say F2, it means you are saying M2 times A. Okay, so if we extend this, we can say M2G minus T1 is already M1A, so we say M1A is equal to M2A. In that case, we can say M2G is equal to M2A plus M1A. Of course, our M2, our A here is on both quantities, so we factor out, it's common to both of them, so we factor out. So we can say M2G is equal to A into M1 plus M2. So that our A, I'll just place this here. So our A, which is the acceleration, because we are calculating the acceleration for both blocks. So the acceleration will give us expression of m2g all over m1 plus m2. So we proceed. Next slide. So like we got earlier, our A is equal to m2g all over m1 plus m2. What is our m2? It is 5 kg. So we say 5 kg times our g, which is 9.8 meter per second square, all over 12 plus 5, all in kilogram. So this gives us 49 kilogram meter per second square, all over 17 kilogram. Of course, this, we take this off, and the acceleration will be 2.88 meter per second square. So we can as well say our acceleration is well approximated to 2.9 meter per second square. This is to 1 decimal place. Then we have to also calculate the tension in the string. The tension in the string will be given by, remember we said T1 is F1, which is this. That's the tension in the string. So our tension will be equal to M1, which is 12 kg, times A, which is 2.9 meter per second square. That gives us around 34.8 Newton. So our tension T is equivalent to 34.8 Newton. So we are going to end this particular lecture series here. In subsequent lecture series, we will just focus on solving more problems using Newton's law of motion. Next lecture series, we'll talk about the Atwood machine. We'll see how we can apply Newton's law of motion, Newton's laws of motion, to handle problems of such. Remember to like my page. Remember to like my channel. Hit the subscribe button for more notifications when I upload more videos. Thank you.